Pigments are molecules that selectively absorb specific colors of light. So what we mean by that is that some colors are absorbed, and then we'll have some colors that are not absorbed. And so some colors are not, and what that means is that these colors that are not absorbed, these are going to be reflected from that pigment molecule. So as it works out, if we're talking about pigment colors, because color tends to be what we really think of when we're talking about pigments, if you had, for example, something that was red, so you had a red pigment, that red pigment, when all of the light colors come in, and when we say all of the light colors, we're really talking about white light. So white light contains all of them. So that white light comes in, and this red pigment is going to absorb all colors except for red. So the color that we see, if we look at that pigment and it looks red, that means that red is the color that is not being absorbed. So all the colors are being absorbed except that the red is basically bouncing back off. And since the red is bouncing back off, when we look at that molecule, red is what we see. So if we're talking about plants, recall that plants are primarily green. And what that means is that green is the color that is not going to be absorbed well by plants, even though we are going to have multiple pigments there really inside of the plants. If we look at chlorophyll A as an example, chlorophyll A has its own unique absorption spectrum. And if you look here, we can see the line for chlorophyll A is showing us that we get a lot of absorption over here in the bluish purple area. And then we have this big hole in the middle where it's not absorbing. And then we see another peak over here around the orange area. Now, some of the colors that are not absorbed very well at all are going to be right here around the 500 nanometers. Even for some of the other colors, even though the line is low, we still get a tiny bit of absorption. So this region right here is where we have pretty much no absorption. So notice that the line color for chlorophyll A is kind of a dark bluish green color. And so we think of chlorophyll A as being a bluish green pigment because it is reflecting those colors, and that makes it appear that way. If we look at the carotenoids as another example, the carotenoids are really a whole group of pigments, and so the line that we're seeing for them here is really showing us kind of just a collective generic absorption spectrum for carotenoids. But with those, you can see that they have a lot of absorption in the bluish purple area, and then they don't have much absorption over here in the, I'll say about 570 and up. So we tend to think of carotenoids as pigments that are yellow, orange, red, something along those lines. And if you think about a lot of your orange or red fruits or yellow fruits, they do contain a lot of carotenoids that give them that color. So all of the pigments that we're seeing here in this spectrum are involved in plants in photosynthesis. So we do want to be aware that photosynthesis involves many pigments. And the reason that it's going to involve so many pigments is that this will increase its efficiency. So it increases efficiency because where one pigment might only be able to absorb half of the spectrum here, if we add in another pigment, we've now broadened the colors of light that we're going to be able to use. And then if we add additional pigments beyond that, again, we've just been able to now cover more of the spectrum of visible light. We've got more colors that are going to be usable for photosynthesis. Now, when you take all the different pigments together and we look at where we don't have much absorption occurring, it is really right here in the middle. So it is in the green area. So the green is not absorbed by really any of the pigments here. And that right there is going to be the reason that plants appear green, or sometimes we say a yellowish green, because there are no pigments there that are able to absorb that green. That means that green is primarily just passing right through the leaves, or in some cases it could be reflected off of the leaves. Here we're looking at two different chlorophyll pigments that are involved in photosynthesis. Both of these are going to be located in the thylakoid membranes, and here we can see the molecular structures for these. Now, it's not necessary to know the chemical structures, but one thing that I do want to point out is notice that both of these, if you look at them, they do have these large hydrocarbon portions, or what we would call hydrocarbon tails. And this is important because these pigments will embed in the thylakoid membrane. And the way that they're able to embed in that thylakoid membrane is that they will be able to take those hydrophobic tails and they can actually insert those into the hydrophobic core of the membrane. The chlorophyll molecules do that. If we look at other types of pigments, they're also going to have long hydrocarbon portions that can embed in those thylakoid membranes as well. Now, this does not apply to all pigments that you would have anywhere, but this is the case for the pigments that are going to be involved in photosynthesis.